In the year 1650, a mathematician by the name of Pietro Mongoli proposed a rather uncanny problem. He was a professional mathematician at the time, and he had also proved the divergence of the harmonic series and also validated the Wallis product, which you might know. What he asked was as follows: what is the value of the sum of the squares of the reciprocals of the natural numbers? And this was no coincidence, because in the book he published, he discussed about several finite and infinite sums. So these sums were a natural consequence to what was going to happen next. He also discussed about a series with the term 1 upon n whole into n plus r, and he gave several list of values which are listed here from his book itself. And these values were the values when this was summed from n equals to 1 to infinity. He had also given answer to the following infinite sum, which converges with sum 1 by 4. But he failed at the problem which has nth term 1 upon n square, and therefore he proceeded to write this as a challenge in his book. At that time, this was really a very hard problem. John Wallis in 1655 from England, Ashford, took it up to himself, but he could only solve it up to 3 decimal places. In Basel, Switzerland, there was another family. Jacob Bernoulli proved that the series converges, but he could not find an exact solution. Now, if you're confused about convergence, do check out the description or just read this definition. Then Christian Goldbach suggested a very strict bound. He proved that it lies between 41 upon 35 and 5 upon 3. We can prove an even simpler bound. Now we only need to show that this series equals to. Consider a unit square divided into two halves. We have 1 by half area each. Now go to the right hand half and divide it again. Now we have 1 by 4. Do it again, we have 1 by 8. Do it again, we have 1 by 16. I think you see the pattern. Now if you keep doing this infinitely and now add all the areas and keep adding them, notice that we will always be inside the area of the square, which is 1. Therefore this entire sum must equal 1, and if you add 1 to both sides, we get the result. No one could solve this even after 80 years. But then came Euler, born in the city of Basel, after which the problem itself is named. In 1734, he actually solved the problem. Here is how Euler solved it. So, step 1, we have to factorize sin x into an infinite product. Step 2, we need to write sin x as an infinite series. And step 3, we need to compare the coefficients of x cubed from both these definitions. So, let's begin. We would only outline of what is needed. So, first write down e to the power z equals to this limit. Change z to iz, and you get this definition. Now remember that sin z is equal to e to the power iz minus e to the power minus iz upon 2i. We can use this definition inside the limit and put it back there. This would give us the following sin z representation. Now, with this value in hand, we can factorize sin x as follows. For any two numbers x and y, x to the power n minus y to the power n can be written like this. Now, this is something which I'm not going to prove. With some substitutions and algebraic properties, we can turn this into the desired product. So check out the link in the description for a detailed overview of how to do this. Now, the series expansion. Consider the following expression. It's a polynomial of nth degree, right? Now, if we wanted to write sin x as a polynomial of nth degree, it would not be possible. This is because a polynomial of degree n has exactly n roots. But if we look at the graph of sin x, we can see the yellow marked points are the roots of the function. Now, these roots are minus 2 pi, minus pi, 0, pi, and 2 pi. You can keep adding them. Even if you were to find more roots, you can simply expand the function further in the x or y direction, and you would get more roots. This simply implies that this is a periodic function and it has infinitely many roots, and therefore it cannot be fit inside a nth degree finite polynomial. Only choice? Infinite polynomials. Therefore, we tend n to infinity, and therefore we get sin x is equals to a limit of this sum. Now, any function can be expanded using Maclaurin series as follows, where you can simply use the derivatives of the function around 0. If we look at a few derivatives of sin x around 0, we would immediately notice that it is periodic and it rotates around 0, 1, minus 1, and 1. We can use these coefficients in the Maclaurin series expansion and put it back there to find out the infinite series representation of sin x. The even terms have all coefficient zeros, and therefore only the odd terms remain. This gives us the series representation for sin x, which is valid for all x belongs to real. We can also do a quick little exercise to see how this polynomial basically matches sin x. Draw the graph of sin x, draw the graph of the polynomials one by one. So take the first term, take two-term approximation, and you can keep on doing this And as we approach more and more terms, you would see that the graph below slowly approaches the shape of sin x. Isn't that fascinating? Now that we have the two representations of sin x, the infinite product on the left and the summation on the right, let's start with the infinite product and try to extract the coefficient of x cubed from it, right? So first write down it as a product in term-wise fashion. So x times 1 minus x squared by pi square and stuff. Notice the x squared terms inside the brackets. Now when you multiply this out, you will first get a term of 1 because all the ones multiply. And then in coefficient of x squared, you will simply get 1 by pi square, 1 by 2 square pi square, 1 by 3 square pi square and everything, because all of those terms also get multiplied with those ones in the other bracket. Now therefore the coefficient of x cube is just that series, and from the right hand side the coefficient of x cube is minus 1 upon 3 factorial. Equate the coefficients and therefore we find out the value of our required series as pi squared upon 6. So I hope you enjoyed the video, and I would try to make videos much better from now on. I'm learning how to do this stuff and put them together. So pardon me for any rookie mistakes that I might have made. So thank you for watching. I'll see you in the next video.